he yesterday expressed about the FRT gravity on a modified gravity. And the Starobinsky lecture. So if you go for the Starobinsky model, so the Starobinsky model is very famous for the R square model. So f of R square, which is also a modified gravity approach. So today what I will do, I will go for a FQLM gravity. So this is a gravity which was proposed by us. The baby is not born till today because it is the paper we submitted the second revision December 10 to JCAP. So it is still under review. So the baby yet to born, and we are hoping to get this baby in next year. So I welcome all the suggestions because still the paper is under review. Okay, so the outline of my talk will be like this. I will go for the introduction of the gravity, but most of you already discussed last 2 days. Then why we are going for the modified gravity. Then I will discuss the types of geometry, what Dawood expressed and Saintan asked about the torsion and the non-metricity. So that basically the geometric trinity of the general relativity. So that I will go for the types of geometry here. After that, I will come to the proposed FQLM gravity, then what about its implications. Okay, so the first question is, what is gravity? So from our childhood, we started the gravity with the falling of the apple. The falling of the apple story by Newton, that is what the starting point of the gravity for everyone. Then coming to Einstein. So Einstein's gravity basically based upon the Riemannian curvature tensor with the famous field equation which he proposed in November 1915, that the left hand side is the geometry and the right hand side is the matter, and based upon the metric he has discussed the action principle. Now these are the observational times. So basically the success of general relativity, which already last 2 days it was discussed, the bending of light, then coming to the Persian mercury, gravitational lensing, gravitational waves, and time dilation. So all last 2 days the talks already discussed about it because they are based upon the GR. Then coming to Einstein. So what is the basically problems in Einstein's general theory of relativity? Why there is a need of new gravity or the modifications of GR? So the dark matter problem, then coming to the cosmic acceleration, and the present cosmological tension, that is particularly H0 and S8 tensions, then quantum gravity, and the singularity problems in general relativity. So based upon these problems, there are various modified gravities proposed from time to time, starting with FR gravity, then Orensky gravity, FT gravity, FQ gravity, and so on. Okay. So if you go for general theory of relativity, basically Einstein's general theory of relativity, which is based upon the Riemannian geometry. So basically the Riemannian curvature geometry, the extension of, so we started with Euclidean geometry, then the need of the Riemannian geometry. So based upon the Riemannian geometry, there is general theory of relativity. Then the extension is f of r, the function of Ricci scala. So the f of r gravity. Then from f of r, there is a coupling gravity known as f of RLM gravity, where LM stands for the matter Lagrangian. Then another one is the f of RT gravity. So T is the trace of the energy momentum tensor. Then f of R phi gravity, where phi is the scalar field. Then f of RT, R mu nu, T mu nu. So starting from FR, these are the extensions of f of R or the coupling gravity. Some are the minimal coupling and some are the non-minimal coupling gravity. So the coupling are based upon the matter Lagrangian LM, then the trace of the energy momentum tensor T, and the scalar field phi. Okay, so these are the extensions based upon the Riemannian geometry starting from general relativity. Now the question is the only geometry which can express the gravity, the Riemannian geometry, or there is any other geometry which can express the gravity? So coming to Weyl geometry. So when Weyl developed the Weyl geometry, then Einstein used the Weyl geometry, the unification of GR and the electromagnetism. So once the Weyl geometry came to the picture, the main question came the affine connection. The affine connection was not used earlier because Einstein's theory based upon the metric. So then this is the question of the affine connection. So coming to the affine connection here, this is the generalized form. So the affine connection contains 3 terms. The first one is the curvature term or the second order Christoffel symbol, which we are used in GR. Then the second one is the torsion, which is known as the contortion tensor, and the third one is the non-metricity. So affine connection has three terms which we use to tell the trinity of geometry in general relativity. So one can go through this Lavinia-Heisenberg's review, which is published this year in physics reports. One can get all the details of the geometry in that review article. Okay, so here this describes the Riemannian tensor, then the contortion describes the teleparallel gravity, and the non-metricity or the deformation tensor describes the symmetric teleparallel gravity. So based upon these three, we have three gravity, which is f of r, f of t, and f of q. And then you can go for the couplings in r, t, and q gravity. So you can get various minimal and non-minimal coupling with respect to this trace, then matter-Lagrangian, and the third one is the scalar field. So what we did in this article, so we proposed a coupling with the q and the matter-Lagrangian LM. Okay, so coming to general relativity, so the RTQ. So in general relativity, this R, which is non-zero, and the torsion and the non-metricity both are 0. Then coming to symmetric teleparallel gravity, so in teleparallel gravity, the torsion tensor is not 0, whereas the Riemannian curvature tensor is 0 and the symmetric tensor is also 0. And coming to symmetric teleparallel gravity, the non-metricity Q is not 0, whereas this torsion and the Riemannian curvature tensor both are 0. So these three are known as the trinity of the geometry in general relativity. So based upon this trinity, we used all the modified theories of gravity. Now what about the base on that? So coming to this curvature, torsion, and non-metricity. So when you go for the curvature, so which is used in general theory of relativity, particularly this Riemannian curvature tensor. So here the direction of the vector changes when it is parallel transport. But coming to the teleparallel equivalent, this torsion based, so the non-closure of the parallelogram. So when you go for this parallelogram, the non-closure of this parallelogram during the parallel transport is attributed to the torsion. And coming to the symmetric teleparallel gravity, the non-metricity. So here the length of the vector changes as it parallel transports. So in parallel transport, the length of the vector changes in the symmetric teleparallel gravity. So this is the base of these three gravity based upon R, T, and Q. Okay, so coming to the new proposal, which we started, actually we started last December, this gravity, and submitted to JCAP, and we submitted this December the second revision. Okay, so this paper is available in archive. So the action with for this FQLM gravity is a coupling of Q and LM, where Q is the non-metricity and LM is the matter-Lagrangian. Then coming to the field equation, so we derive the field equation here, and the FQ and FLM, which is the derivative with respect to Q and LM, is used here, and this is the superpotential. Now coming to the Einstein tensor form. So in Einstein tensor form, this is Gij plus half Gi. So this is the field equation, and the FQLM Klein-Jordan equation also we derived in this, taking the scalar field, we derived the Klein-Jordan equation in this article, and we also studied the mass of this effective and the start taking with scalar field particle. So another thing is what we did, so this FQLM gravity can be reduced to general theory of relativity, and also this can reduce to FQ gravity. So when you make this for minus Q plus 2LM, then we get the Einstein's field equation general theory of relativity, and if you make this Q as a function of Q plus 2LM, then this FQLM will reduce to the FQ gravity. So one can reduce this FQLM gravity to general theory of relativity and also FQ gravity. Okay, so coming to the energy momentum tensor, because if you go for the conservation equation, mostly the conservation equation fails in all the coupling gravity. If you go for FRT gravity, FQT gravity, or you go for any coupling gravity, in most of the coupling gravity, the conservation of the energy momentum tensor fails. So here we have taken the energy momentum tensor with the balance equation, which is given here, and in the hypermomentum density we used, and what we did here, we calculated this dynamics of the massive particles and the tensorial form we checked. So once we get the form, if it is 0, then it is conserved, and if this equation is not 0, then it is not conserved and the energy transfers. So this is basically the energy balance equation. Okay, so coming to the Friedman equations. So the Friedman equations in this FQLM gravity, starting with a FRW metric and the energy momentum tensor of this form of a perfect fluid. So this is the first generalized Friedman equation, and this is the second generalized Friedman equation in FQLM gravity. Then coming to GR again, so these are the two Friedman equations, so one with effective density and another with effective pressure, and these two, and this is the conservation equation. Then the same thing, we generalize these two terms in first Friedman and second Friedman in FQLM gravity. And so going for this gamma, so this gamma is the basically the conserved, so whether it is conserved or unconserved. So coming this balance equation, so if this gamma is greater than 0, then the energy particles are increases, and if the gamma is less than 0, then the particle decay due to the coupling. And if you make this gamma is 0, then the conservation equation satisfied. So it is the energy conservation equation. Then coming to the deceleration parameter, which tells about the acceleration or deceleration of the model, the deceleration parameter Q is given in this equation for this FQLM gravity. Okay, so what we did here, we started with two models. We derived these field equations from the geometry, then we went for the action. Then after that, we tested this FQLM gravity with two models. The first model is a linear model, and the second form is a nonlinear model. So in this linear form, so there are two parameters, alpha and beta. And here it is a square form, so the nonlinear form in the model B. And the matter Lagrangian we have considered are the pressure, which is gamma minus 1 into rho. If you take gamma is 1, then you can get the matter form. And if you take gamma is 4 by 3, then one can get the radiation model. So both this matter and radiation model, you can obtain from this LM, considering gamma is equal to 1 or gamma is equal to 4 by 3. Okay, so in these two models, these are the two Friedman equations. And first we check the, so if you go for this linear model, so what we saw in the linear model, the energy momentum tensor is conserved. So we got the conserved equation, so this gamma is 0 here. Where we just kept the gamma because it is not conserved, the balance equation. Okay, so what we did after that, so already yesterday Professor Suresh discussed about the Hubble tension. So he has showed various data sets what the present cosmology we used in the cosmological models. So in this article, we went for the statistical analysis, the MCMC analysis. So we consider the supernovae data and the Hubble data plus supernovae and biodata. So this is the combined data sets and this is the supernovae. So in the first model, the value for the H0, we got 72.4 and 72.5 for the combined data sets. So these are the alpha beta, the model parameters, which we got from the 1 sigma and 2 sigma contour plots. Then if you go for this Q0, so the values for the Q0 in the first model is coming to minus 0.44, and the transition from the deceleration to acceleration, which happens at 0.46 and 0.56. Okay. So coming to the second model, in the nonlinear model, so in the nonlinear model, the transition happens in 0.47 and 0.56, which Professor Swami yesterday told to Suresh that the transition should come between 5 to 6, 0.5 to 0.6. So exactly we are getting this transition in the combined data sets is 0.56 in both the models, in the linear model and the nonlinear model. And the values of the present deceleration parameter Q0 is coming at minus 0.44 and minus 0.48. So it is just similar results in both linear and nonlinear models. And the values of alpha, beta, gamma, as I mentioned, we used, we took from the 1 sigma and 2 sigma contour plots, the 68% accuracy. So these are the two contour plots for the linear model and the nonlinear model. Okay, so these contour plots gives us the values of H0, alpha, beta, and gamma. Okay, now coming to the comparison. So what we did, we compare our statistical values with the chi-square and the AIC, BIC criteria. So As you see in the table, so generally the del IC and del VIC. So the del AIC and del VIC values for the lambda CDA model is 0. So the minimum values of the del IC and del VIC is always the more accurate towards the model. So in our model A and B, we got the del IC and del VIC values with 2.13 and 3.4. So 2.0. So it is the minimum values for the del IC. So it shows that our model is fitting to the lambda CDM. Now coming to the key parameters, particularly the density and the deceleration parameter and the equation of state parameter. So if you go for the density in both the models, so the rho bar is basically we have taken rho by 3h naught square. So the density you can see it is positive throughout the inverse. So the lower values to higher values of the z, and both then same in the second model. Now coming to the behavior of the deceleration model. So you can see the deceleration parameter. It has a transition from deceleration to acceleration, which approaches to lambda CDM, and is value 0.48 and 0.56 for both the Hubble data sets and the combined data sets. Similarly, in the second model also, there is a transition from deceleration to acceleration. Now coming to the equation of state parameter, the effective equation of state parameter omega. So in this case also you can see it is there in the acceleration phase, and it is approaching to the lambda CDM. Now what we did, so as I mentioned, we have discussed about the Klein-Jordan equation with the scalar field phi. So we have taken the mass of the scalar particles, and we discussed in both the models. So the effective mass square, where this initial mass square plus xi, and this, so this xi is the coupling parameter. So for this xi, the coupling parameter, we have taken the range of this xi, the coupling parameter, from -1 to 1. So you can see, so the bold line is for xi is equal to 0. So if we see when xi is negative, we are getting it is the values are coming negative for this effective mass square, and the values for xi, when it is positive 0 to 1, you can get the positive value. So the similar behavior we are getting in both the models. So this is for the effective, so this is actually the effective mass square versus the initial mass in these two plots. And in the next plots, what we have taken the ratio of the effective mass square by initial mass square versus the redshift parameter z, and the z we have taken from -1 to 3, where the same the coupling parameter zeta is from -1 to 1. Here also you can get the same behavior. When you go for zeta is negative, -1 to 0, you are getting this negative. So then this is the values for the positive zeta. Okay, then coming to the comparison of this model, our model with the lambda CDA model with the Hubble data set. So coming to the h of z versus z, so you can see our model is similar. So with the bold one is the lambda CDA model, the black line. Then this model A and model B are with the color lines. So it's you can see this model is approaching to the lambda CDM with the comparison. Then in the next figure, we have taken the distance modulus, the mu of z. So the mu of z versus z, you can see the error bars and the comparison with the lambda CDM. Okay, so coming to the final remarks. So we have extended this general relativity to a modified non-metricity based gravity, which we named as FQLM gravity. Then we derived the FQLM field equations, and we calculated the tensor balance equation, then the modified Klein-Jordan equation, and the Friedmann equations. Then we solved the Klein-Jordan equations for both the models A and B, and we discussed about the effective mass square. Then solving the Friedmann equations for both the models A and B, we discussed the statistical analysis of the contour plots, taking the Hubble data sets and the combined Hubble, bio, and supernovae data sets. And what about the cosmological evolution through the deceleration parameter and effective equation of state parameter. So though the original paper is not published, there are extensions which are already published. So these are the two articles from in FQLM gravity which are already published in Physics of Dark Universe and Journal of High Energy Astrophysics. And there are 3 articles available in archive, which are based upon the FQLM gravity and its extensions. So this is the present development by various authors in the literature. So now coming to the future, so one can go for the matter geometry coupling with various impacts. Then one can study the dark matter, neutron stars, photon rings, the Raychaudhuri equations. Then all the astrophysical objects like boson stars, graha stars, the negative singularities, wormholes, one can study on this. So there are many things we can explore once this article is accepted in JCAP. So these are the collaborators. So mostly the calculations are done by MSc students. So Ayush is a MSc student who came to me for internship, and Simran is my PhD student. She is a JSPS postdoctoral fellow at YITP now, and Professor Harko, who proposed FRT gravity, also mentored us in this FQLM gravity. So these are the sources for the pictures, and these are some references. So thank you. So any comments and suggestions are always welcome, because this gravity we propose, which is not published, we can interpolate it.
Okay. Yeah. Questions?
I have a very basic question.
Yes.
So you have the Q, T, and LM. Right?
Yes.
So is there any motivation behind Q and LM, the combination, and why not we can have various combinations? So is there any limitations or any?
Yeah.
Just
So
trying to understand.
basically, that is what I go 1 minute. Yeah. So if you go for this, okay. So generally based upon the Riemannian geometry, from GR the FR was started. Then from FR the coupling started, as I mentioned. The couplings are based on this matter Lagrangian. Then so this is the trace, the T trace of the energy momentum tensor, and the scalar field. Even if there is a article f of r, t, and r, so the combination of r mu nu and t mu nu. Okay. So these are basically the coupling. Then you can go for the linear form and nonlinear form to get the minimal and non-minimal coupling. So all the couplings are based upon the three things: trace, then the matter Lagrangian, and the scalar field. Okay. So the same thing you can get in the f of t and f of q. So f of qt is already there, which is proposed in 2021, and we extended the f of qt to f of qln.
I see. Okay. Understood. Thank you. And maybe can I ask one more?
Yeah.
So and then the model A and B.
Yes.
Again, I'm just trying to understand the specific choice.
Yeah.
And then
So basically,
they are
that's what
different.
actually I expect. That's what I kept I am not told that time. So if you go for these two models, so there are two model parameters, alpha and beta. Fine. So always there is a question, because I used to get these questions why you have taken two model parameters, alpha and beta. Because the minimum of if you take minimum number of model parameter, it gives better result. So why you have taken two model parameters here? The idea of the two model parameter is, if you make alpha is 1 here, fine, then this will reduce to GR. Because I told that GR, we can get GR from minus Q plus LM, like beta will be. So what is the use of beta? Particularly beta gives a cosmological constant. We kept beta to get the cosmological constant. Fine. So if you make alpha is 1, so this will reduce to GR, where beta will play the role of cosmological constant. Okay. So if you take Q is a function, right? Then you can get the FQ gravity. Okay. So then to get the linear and nonlinear models, so here we have taken LM and here we have taken the LM square. So we just want to check whether the model fits for both linear form and the nonlinear form. One can do another question. So here we have taken the linear of Q. One can go for the nonlinear of Q, because you want to get the FQ. So once you get, so this one, the first model, easily one can reduce to GR. So to get f of Q, so this Q can be considered as a function of Q. So if you go for function of q, then you can take some q square, q plus something, then take any functions of q, so that you try to reduce this model to FQ gravity. In the first case, what we did, we tried to reduce these two models to GR, where beta plays a cosmological constant, and if alpha is 1, then it will go reduced to GR.
There are no more questions. Sorry.
Yeah.
Okay.
If
Okay, yeah, sure. So, is there any improvement for the nonlinear model B? Like, because, or it's just both of them fit the data well, it looks like.
this one.
Yeah.
Yeah, so that's what I told. So basically, what we take the nonlinear form in the matter Lagrangian. Based upon the matter Lagrangian, we have taken the nonlinear form. One can take on the Q. What you can make, you make LM both the places, keep 2 LM, and take Q and Q square. So first model you can take Q, second model you can take Q square. So that you will get another nonlinear T where it is a function of Q. Right? And if you go for higher powers, then your differential equation will become more critical and getting a solution will be more complicated. So that case, then you have to go for solutions in numerical. You cannot get the exact solution, and you have to go for the numerical solutions. Because once you go for higher orders, then it gives difficult solutions.
Okay, let's thank Professor Sahu again.
Thank you.
So the next speaker is Sumanta Chakravarti, and has an interesting title, Tides, a Story of Love. So let's wait for his lovely talk.
Okay. So I guess very good afternoon, because it is just past 12. Thanks to Sheshadri for chairing the session.